Welcome to the very first deep dive of our brand new series, First Principles of Materials and Its Science.
Excited to have you here.
So today, we're diving into the world of material science. Specifically for you, actually. You want to know more about the fundamentals and some more, well, advanced concepts. Particularly, you seem interested in carbon and its different forms.
Yeah, it's a great area to explore. Material science is about the building blocks of, well, everything, understanding how those building blocks work, how they're arranged, how they interact. That opens up a whole new way to see the world.
Building blocks of the world. I like that. And, you gave us a source that uses a really cool example. Diamond and graphite, both made entirely of carbon, but wow, such different properties.
Allotropes, that's what we call them. Different forms of the same element. The structures are different, so the properties are unique. Diamond, it's got that super strong 3D structure, tetrahedral it's called. That's what makes it so hard, the perfect material for cutting tools.
And then you've got graphite, the stuff in pencils, which is soft and slippery. Hard to believe they're both made of the same element.
I know, right? But the difference is all in how those carbon atoms are bonded. In diamond, each one's got these strong bonds with four neighbors creating that rigid network. But graphite, each carbon atom bonds strongly to just three others in a layer, leaves one electron free to roam around.
So those free electrons cause the weak bonds between the layers, making graphite, well, soft and slippery. But the source also mentions some other forms of carbon, amorphous carbon, Buckminster fullerene, that's C60, and graphene. Could you tell us a bit more about those?
Sure, amorphous carbon, it doesn't have that defined crystalline structure like the name suggests. You find it everywhere, from charcoal to soot. Buckminster fullerene is more like, well, picture a soccer ball, but on a molecular scale. It's a fascinating molecule made up of 60 carbon atoms.
Wow. So carbon can form these really intricate structures. And then there's graphene. I hear that word a lot these days. The source says it's basically a single layer of graphite, just one atom thick.
Yeah. Graphene is pretty exciting stuff. Super strong, flexible, and great at conducting electricity. So naturally, there's a lot of research focused on it, especially for electronics, sensors, and even things like energy storage.
So we could be talking about like breakthroughs in technology, and it all comes down to what? One form of carbon.
Exactly. And that's what makes understanding the fundamentals of material science so important. It's the key to unlocking all these possibilities, seeing what these building blocks can really do.
Well, speaking of building blocks, you also gave us this source that really dives into the specifics of graphite. It's called Graphite Properties and Characteristics. Looks like a gold mine of information.
It is. It goes way beyond the basics. We talked about those already. This gets into the nitty-gritty details of what makes graphite so versatile. Density, porosity, hardness, and a whole bunch of thermal and electrical properties.
So density and porosity, I always think of graphite as like this solid block, but the source mentions pores, voids. How does that work?
It's all about how the atoms are arranged and those spaces between the graphite particles. Those voids are what determine the density. In fact, most commercial graphites never reach the theoretical maximum density because of them.
So even though it looks solid, there's a lot of empty space in there. And that's where porosity comes in.
Exactly. And there are different types of porosity, too. The source talks about open and closed porosity. Open porosity, it's like a sponge. Those pores are connected. Closed porosity means the pores are isolated. Integrous graphite, they mention that in the source, is known for its fine, open porosity. Makes it great for modifications like sealing or purification.
Okay, so we've got density, porosity. What other cool properties should we know about?
Well, let's talk about hardness. It's not just about, like, scratching something. It's about how a material resists deformation, abrasion, indentation, how easy it is to machine.
So materials hardness tells us a lot about how we can actually use it.
Yeah. Now, graphite, it's got this high compressive strength, meaning you can squeeze it with a lot of force before it breaks down. And get this, unlike most materials, its strength actually increases as it gets hotter, up to 2,500 degrees Celsius.
Wow, that's pretty wild. It gets tougher the hotter it gets. So are there other types of strength we need to think about?
Yeah, there's flexural strength. That's its resistance to bending. The source explains how even tiny flaws can affect graphite's strength, and why the structure of integrous graphite is very fine and uniform makes it super strong in that way. It's also isotropic, meaning it's strong no matter which direction you bend it.
So no matter which way you bend it, same strength. That's cool. What about tensile strength? How well it resists being pulled apart?
That one's a bit harder to measure accurately. Graphite is brittle, so it tends to just snap under tension. But like with the compressive strength, integrous graphite's tensile strength also goes up at higher temperatures. Pretty unusual, especially compared to metals.
Okay, so we've got hardness, compressive strength, flexural strength, tensile strength. Anything else?
We've also got the modulus of elasticity. This is all about stiffness, how much a material will deform under stress. It basically reflects how strong the bonds are between atoms, and it's connected to the melting point. High melting point means strong bonds and a stiffer material.
Makes sense. What about porosity? How does that factor in?
Porosity can really affect the modulus of elasticity. More pores mean a less dense structure, which usually means a lower modulus.
Hmm.
And again, integrous graphite's isotropy shines here. Consistent modulus in all directions.
I'm noticing a theme here. Consistent structure, consistent properties. Got to be a good thing for manufacturing and engineering. But we've been talking a lot about, the mechanical stuff. What about heat and electricity?
Great point. The source covers that too. Let's start with electrical resistivity. It explains why some graphites are better at conducting electricity than others. Temperature and density are both important here.
I remember from, basic physics, conductors, insulators. Where does graphite fit in?
Graphite's a good conductor, but its conductivity depends on those things I mentioned, temperature and density. Generally, higher temperature means lower resistivity, so better conductivity. And denser graphites are better conductors too.
Makes sense. And since we're talking heat and electricity, what about thermal conductivity? How well does it conduct heat?
This is where things get really interesting. Graphite's thermal conductivity actually decreases at higher temperatures. That's not what usually happens with materials. Usually they get better at conducting heat as they heat up, but graphite, not so much.
Graphite, always keeping things interesting. But given that it's so strong at hot temperatures and has these, unique thermal properties, I'm guessing it's used in some pretty intense applications.
Oh, yeah. The source hints at some uses in high-temperature stuff like crucibles and furnaces. But before we jump into that, let's talk about a property that's closely related to thermal conductivity. Thermal shock resistance.
That sounds andest.
It is. It's all about a material's ability to handle sudden temperature changes without cracking or breaking. And, you guessed it, integrous graphite is a superstar here. The source mentions it can handle a 1,000 degrees Celsius temperature drop without any damage.
Seriously. So you could take a piece of this graphite, heat it until it's glowing red, and then dunk it in ice water, and it wouldn't shatter.
Pretty much. That's why it's so valuable in places where temperatures change rapidly. Aerospace components, certain types of heating elements, that sort of thing.
Yeah, I can see how that would be important in those environments.
Okay.
So it's all starting to come together. What else is there when it comes to heat?
Well, there's specific heat. It's the amount of heat energy needed to raise the temperature of a certain amount of material by a specific amount. The source talks about how this relates to graphite's use in high-temperature applications, where it can absorb a lot of heat without big temperature changes. That's a big advantage.
Okay, so it could really take the heat. Any other heat-related properties?
There's also emissivity. It's basically a measure of how well a material radiates heat. The source talks about the role of surface roughness here and how it's important in fields like aerospace and heaters. A rougher surface will radiate heat better.
So we've covered a lot. Density, porosity, strength, heat resistance. All these properties make graphite pretty darn versatile.
Exactly. But there's one more property in the source we should talk about, ash. It's all about the impurities present in graphite. Now, integrous graphite is known for being very pure. They use a purification process that removes almost all of those impurities.
So they're basically cleaning it up, getting rid of the unwanted stuff. Why is that so important?
Well, impurities can mess with a material's properties. They can weaken it, make it more likely to oxidize, react with oxygen, even change its electrical and thermal behavior. Integrous graphite has ultra-high purity levels, often less than 5 parts per million of impurities.
Wow, that's crazy pure. And the source says that this purity is partly thanks to that fine porosity we talked about.
Exactly. That open porosity makes purification really effective. But even pure graphite can still react with oxygen at high temperatures. That's called oxidation. The source explains how Integrous uses a special oxidation inhibitor to protect their graphite from degrading in those harsh environments.
Like a shield to protect it from oxygen. Clever. But I have to admit, all these properties are starting to make my head spin. Why should we, as listeners, care about all these details about graphite?
I get it. It's a lot of information. But here's the key takeaway. These properties are what make graphite so incredibly useful in so many different applications. Think about what we've talked about. High strength, even at high temperatures. great thermal conductivity, resistance to thermal shock, a high melting point.
Right. And you mentioned earlier things like crucibles and furnaces. I can see how those properties would be important there.
Exactly. Crucibles, for example, are these containers that are used to melt metals and other materials at really high temperatures. You need a material that can take that heat, resist chemicals, and not contaminate what's being melted. Graphite ticks all those boxes.
And furnaces also operate at high temperatures, so I imagine graphite is used in those as well.
Yep. And its good thermal conductivity makes it perfect for transferring heat efficiently. But it's not just crucibles and furnaces. The source mentions it being used in electrical applications too, like electrodes and batteries.
Makes sense.
Yeah.
We talked about its electrical conductivity earlier. And remember how we said it's also used as a lubricant? That's got to be because of those easily sliding layers, right?
Exactly. Those weak bonds between the layers mean they can slide past each other with very little friction. That makes graphite a really effective dry lubricant. It's used in everything from locks to machinery.
Wow. So we've gone from, like, the atomic structure of carbon to real-world applications in crucibles, furnaces, batteries, even lubricants. That's quite a journey. But I'm curious, are there any more, I don't know, advanced concepts related to graphite that we should know about?
Definitely. The world of graphite is huge. There's nanotechnology and graphene, for instance. Remember we talked about that earlier. It's revolutionizing materials science with its amazing properties.
You mentioned it could change the game for electronics and sensors. What else is there to know?
Well, imagine materials 1,000 times stronger than steel, but also incredibly light and flexible. Imagine electronics that are way faster and more efficient than anything we have now. That's the promise of graphene and its derivatives.
That's insane. It seems like we're just scratching the surface of what's possible with this stuff.
We are. And then there's the whole world of carbon fiber composites, where graphite fibers are embedded in another material, creating these incredibly strong and lightweight materials. They're used in everything from airplanes to bicycles to sporting goods.
So you're taking the already impressive properties of graphite and making them even better by combining it with other materials.
Right. Carbon fiber composites are a perfect example of how powerful it can be to combine different materials. And then there's graphite's role in emerging technologies like energy storage and even water purification.
It sounds like the potential applications for graphite are limitless.
They really are. And as research continues, we're likely to see even more innovative uses for this incredible material.
Well, I'm definitely hooked. Graphite has gone from being the stuff in my pencils to this amazing material that could shape the future. And it all started with understanding those first principles of materials science, how the arrangement of atoms determines a material's properties and ultimately its applications.
I'm glad you see the connection. That's really the core of materials science. Understanding the fundamentals to unlock the potential of materials. It's really amazing. We started with those tiny carbon bonds, and now we're talking about applications that shape our lives. It shows how materials science connects that basic understanding to the things we actually see and use every day.
I know, right? This deep dive into graphite has really opened my eyes. I never thought something as simple as pencil lead could be so impactful.
I hear ya. The source you provided really shows how many different ways we can use graphite, from high-temperature environments to electronics.
It's like graphite is a jack of all trades.
Yeah, good way to put it. And when you think about all its properties, it's easy to see why. The high melting point, the strength at extreme temperatures, it's a real workhorse. Then there's the electrical conductivity, which is important for electronics and energy storage. And of course, those lubricating properties we talked about, all thanks to that unique structure.
Understanding those properties is key, right?
Yeah.
The source really goes into detail about how those properties are measured and compared.
It does. It talks about the specific test methods. For example, to measure compressive strength, they apply a squeezing force to a graphite sample until it fails. That tells you how much pressure it can handle.
And we talked about flexural strength, its resistance to bending. The source mentioned how sensitive that property is to any flaws or imperfections.
Yeah, even a tiny crack can weaken the graphite, making it break under less force. That's why the uniformity and fine structure of integrous graphite are so important. It minimizes those weak points, leading to higher strength and reliability.
Makes me think of building a house. You want to make sure the bricks are strong without any cracks that could weaken the whole structure.
Great analogy. That attention to detail is crucial for making sure graphite can perform well in demanding applications.
We also talked about thermal conductivity and how it's measured. The source mentioned using a laser to heat a sample and then seeing how quickly that heat travels through it.
It's a pretty cool technique. And those measurements show how graphite's thermal conductivity changes with temperature, decreasing as it gets hotter. Most materials don't do that.
Right, another one of those quirky things about graphite. And speaking of quirky, we can't forget about thermal shock resistance, how well it handles sudden temperature changes. The source talked about a test where they heat a sample and then rapidly cool it to see if it cracks.
And Integris graphite, with its fine-grained structure and those interconnected pores, does incredibly well in those tests. It can handle some crazy temperature drops. It really adapts to those changes without breaking.
It's like it has built-in shock absorbers for heat.
Exactly, and that's a big deal in applications where temperatures fluctuate a lot, like in aerospace components or certain furnaces.
As we go through these properties and test methods, it strikes me how they're all connected, like a web where each property affects the others.
That's a really important point. You can't just look at one property in isolation. You have to think about how it interacts with the others and how those interactions might change depending on the environment or the application. Remember how we talked about density affecting both electrical and thermal conductivity, and how porosity affects strength and even the purification process?
Like a multi-dimensional puzzle, where each piece is a property and you have to understand how they fit together to see the whole picture.
Exactly. That's why having detailed information like what's in this source is so valuable. It gives us a much deeper understanding of those relationships and helps us make better decisions about how to use a material like graphite.
Speaking of using graphite, we've talked about some of the common applications, but I'm curious, are there any less obvious or emerging uses? What's next for graphite?
That's a good question. The source hints at some interesting possibilities. It mentions batteries, which are becoming more and more important as we look for better ways to store energy. Graphite's ability to store and release electrical charge makes it a key part of many battery technologies.
Right, we're seeing this big shift towards electric vehicles and renewable energy, and those technologies really depend on good batteries. So graphite is playing a crucial role there.
It is, and the demand for graphite in batteries is only going to increase. But it's not just energy storage. The source also mentions things like aerospace and even nuclear engineering.
Those sound like some pretty specialized applications.
They are. Graphite's high thermal conductivity and resistance to radiation make it suitable for certain parts in nuclear reactors. And in aerospace, it's lightweight but strong, especially when it's used in carbon fiber composites. That helps make aircraft more fuel efficient and durable.
It's incredible how one material can be used in so many different industries.
It really is. The source even hints at some cutting-edge applications using graphene, that single-layer form of graphite, in electronics, sensors, maybe even medical devices.
Oh yeah, graphene. We talked about that
Uh,
earlier. It's like graphite 2.0.
Exactly. Researchers are finding new ways to use its incredible properties all the time. Imagine flexible electronics, ultra-sensitive sensors, even new materials for tissue engineering. Graphene opens up so many possibilities.
It seems like the more we learn about graphite, the more we realize its potential. And the source does a good job of presenting those possibilities, but also highlighting the challenges in areas where more research is needed.
Absolutely. For instance, it talks about how important it is to control the purity and microstructure of graphite to get the best performance. And there's a lot of research going on to develop new processing techniques to make even stronger, more durable, more versatile graphite materials.
Yeah, so there's still so much more to discover and explore. It's not just about using what we already know, it's about pushing the boundaries of what's possible.
That's what materials science is all about. It's constantly evolving. And graphite is a great example of a material that keeps surprising us.
It's definitely inspiring. This deep dive has given me a whole new appreciation for graphite. But before we get too carried away thinking about the future, let's bring it back to the key takeaways from our discussion today.
I think a major takeaway is just how versatile graphite is. It's a material that's used in everyday objects and cutting-edge technologies. From a simple pencil to a high-performance battery, graphite is making a difference.
And we learned how its properties, all of them from density and porosity to strength and thermal conductivity, come from its unique microstructure, the way those carbon atoms are arranged and those tiny spaces between them.
Exactly. Understanding those properties is key to unlocking the potential of graphite. We also saw how those properties are all interconnected, how each one affects the others. That creates this complex web of interactions that determine how graphite will perform in different situations.
And we talked about all the different ways graphite is used, from the well-established applications in crucibles, furnaces, and lubricants, to the emerging potential in batteries, aerospace, and even nanotechnology, with graphene?
It's a good reminder that materials science isn't just about understanding the basic building blocks of matter. It's about using that understanding to make things better.
Well said. And speaking of making things better, I'm curious about your thoughts on this. With the demand for graphite increasing, especially for batteries and other technologies, are there any concerns about sustainability or the environmental impact of graphite mining and processing?
That's a really important question, and one we should definitely be thinking about. The source material doesn't go into a lot of detail about that, but it's definitely something people are paying more attention to as the demand for graphite grows.
Right, we've seen similar concerns with other materials that are used in new technologies, like lithium for batteries or rare earth elements for electronics.
Exactly. As we try to create a more sustainable future, it's essential to think about the entire life cycle of a material, from where it's mined and how it's processed to how it's eventually disposed of or recycled.
So even though graphite has so much potential to help us solve some big challenges, it's also important to make sure that how we produce and use it is good for the environment.
Absolutely. We need scientists, engineers, policymakers, and industry leaders to work together to develop sustainable mining practices, efficient processing techniques, and effective recycling strategies.
Like a holistic approach to material science, one that considers not just the technical aspects, but also the environmental and social impacts.
Wouldn't agree more. And that's something we'll continue to explore in future deep dives as we learn more about the fascinating world of materials and how they affect our lives.
Well, I think we've covered a lot of ground in this second part of our graphite deep dive. We've talked about its many applications, the challenges and opportunities, and the importance of sustainability as we unlock its potential.
And we saw how those fundamental properties we discussed earlier, density, porosity, strength, thermal conductivity, all those things are really what make graphite such a versatile and valuable material.
But our exploration of graphite isn't over yet. There's still so much more to discover. As we wrap this up, I keep thinking about that diamond and graphite thing.
Yeah.
Both carbon, but so different.
It really shows you how those atoms are arranged, that microstructure. That's what determines the properties and how we can use it.
Diamond, it's all about hardness, brilliance. But graphite, with those layers, it's slippery, its strengths are totally different.
And it all comes from carbon, the same element, the basis of life itself, right? It's kind of crazy. Even simple elements can make such a variety of materials.
It makes you think, what else is out there, waiting to be discovered?
Oh, tons of stuff, I'm sure. Materials with amazing properties we haven't even dreamed of yet. That's what's so cool about material science. There's always something new.
I'm already looking forward to our next deep dive. But before we go, let's sum up what we've learned about graphite. Density, porosity, strength, heat, purity, it's a lot. What would you say are the key things that make it so useful?
It's that combo, you know?
Yeah.
High strength, even at those crazy high temperatures, great thermal conductivity, and that resistance to thermal shock. It's a game changer, especially where other materials would just fall apart.
And those properties come from its structure, those carbon layers and all those little spaces between them.
Yeah. That porosity is what gives it those special properties, and it also helps with purification. That's why integrous graphite is so pure.
And we can't forget about how well it conducts electricity, which makes it so important for batteries and other electrical things. Plus, those slippery layers make it a great lubricant for all sorts of mechanical stuff.
It really is amazing stuff. And with nanotechnology and graphene, the future of graphite is looking pretty bright.
I'm fascinated by graphene, that single layer of graphite. It's like graphite, but supercharged.
Exactly. Flexible electronics, super efficient solar cells, medical devices, who knows what else. It's all about using materials science to solve problems and create new things.
I'm convinced. Graphite is way more than just pencil lead. It could be a key to the future. And it all starts with understanding those basic principles, how the structure affects the properties, and how those properties determine how we can use it.
That's the foundation. That's what we're trying to do here, give you the tools to explore this amazing world of materials science.
We've covered a lot, but there are so many other fascinating materials out there, each with its own story.
Definitely. And we can't wait to dive into those with you in future episodes.
So until our next deep dive, keep exploring, keep asking questions, and stay curious. There's a whole world of material science out there waiting to be discovered.